Thanks very much to the organizers for having me here, and thank you also for actually coming here. So as Jacques Artier said, there will be hypergeometric afternoon, so I'd like to start off by showing you some arithmetic background of a special type of hypergeometric functions, which is the following. So this is a generalized hypergeometric function. It has parameters halves and parameters ones. And you know, well, maybe I should, we have seen it earlier, that this symbol, half choose n, stands for basically the so-called rising factorial. So this half n simply means you put a half here and keep on adding factors, each increased by 1 until you have precisely n factors. So it's a generalization of the factorial symbol. If you have only d as 1, then it's just a simple 1 over square root of 1 minus z, which you see there. However, we make it more interesting by putting a d up there. This is also precisely the type of hypergeometric function that you have seen in Frédéric Jouet's talk. Up to a normalization of z, it's the same thing. D is going to be an arbitrary number, and for the moment I will always take it even to avoid slight complications. Well, you know it satisfies a hypergeometric differential equation, which I shall recall. It's this one. And theta stands for the derivation z times d to the d dz. It's a very simple-minded differential equation. And let me first give you a little exercise. It has a very nice symmetry property, namely that if f is a solution, then it turns out that if you change the variable z into 1 minus z and you multiply with z to the minus a half, then this new function will also satisfy the same differential equation. So this is a symmetry which has to do with the interchange of the parameters half and the parameters 1, which you have below. And so this is a nice symmetry. We're going to be using it in a moment. So this is also a solution. Now the game that I like to play is to look at things p-adically. So we're going to look at some p-adic aspects of this hypergeometric function. And what we're going to do is basically take up this power series, but expand or truncate it. So we take the first, and I should say that p is going to be an odd prime. S is going to be some integer which is greater or equal than 1, and we're going to study the truncation of this hypergeometric series. And so we take the same coefficients again, to the d n factorial, to the d z to the m, except that we stop at z to the p to the s. This is a truncated function. And it turns out that this has some interesting properties. This follows from the p-adic theory of Dwork in his article, P-adic Cycles. He makes a very interesting observation regarding these truncations. So for example, if you take an argument which is going to be a p-adic integer, units preferably, such that the fp of z0 is also going to be the p-adic unit. Then Dwork showed a couple of very interesting congruences, namely that if you take the truncated p to the s plus 1 at the point z0, divide by p to the, we're going to do congruences, so I have to explain the idea of division in a moment. But Dwork showed that really you have this congruence modulo p to the s for all odd primes and all s greater or equal than 1. And I write, of course, well, I take a division, but of course, with this, I mean that you take the mod inverse modulo p to the s of this expression. And the point is, because we assume that this is a unit, by induction on this relation, you can check that all the fp to the s's of z0 are going to be p-adic units. So therefore, we have this very interesting relation. And so this is a congruence that, well, it's basically you have the same sequence all over, except that the index s goes up by 1. So basically you have a Cauchy sequence, which is a p-adic Cauchy sequence, and of course there's a limit. And let's give this limit a name. Let's call it fp z0, and that's going to be the p-adic limit as s goes to infinity of this ratio. And this quantity is somewhat of a mysterious quantity. Dwork calls it the p-adic unit root. And of course, we have to explain what it is a root of, basically, but that will come somewhat later. Essentially, this function here is really, so I can make a slight comment on it, without making it very much clearer. Anyway, this value here is basically, if you take this power series that we had over here, divide by fp z to the p, and this power series can be continued p-adically to the boundary of the p-adic unit disk, and you can continue p-adically to z is equal to z0. And that will give you, well, that will give you basically this value. So basically, this is the p-adic analytic continuation of this quotient of functions. Well, it's not much more meaningful, I understand that, but for people who want to know about this, this is what it is. So I'm going to explain this unit root property in a moment in a better way. So now that we have this limit, you can of course easily see that we have the following congruence, that for all s's, we have that fp to the s of z0 is equal to fp z0, fp to the s minus 1 z0 mod p to the s. And moreover, if we take the particular case that s is equal to 1, we get the congruence fp z is equal to fp z0. And if s is 1, well, basically we have the zeroth truncation, which is basically the constant. So really, this is just, this will be trivial, it will just be 1. So we get this congruence in the case s is 1. Now, it's this congruence that I like to concentrate upon and give a couple of examples where we actually see this congruence happen, and even some more surprising phenomena. So what we're going to do now is take a special value for z0. I will take the value 1. And as an example, the starting example, we take d is 2. So basically we have the squares of these strange coefficients there. And I think for people who know, this basically satisfies a second order differential equation, which is a period of the Legendre family of elliptic curves. So it has a geometrical context. And in the case when d is 2, we find that fp of 1, well, in the specific case, we know what this number is. It's simply this Legendre symbol, and we get this congruence. And now well, this is of course all rather standard, but the great surprise is now that essentially, not only does this congruence hold modulo p, it holds modulo p squared. It's a little extra surprise. And it turns out that in number theory, in areas like this, it turns out that very often you get congruences which are stronger than what you expect on the basis of general theory. And that's the reason why people call them supercongruences. And that's the name I like to add here. This afternoon also the name of hypercongruences came up, but I'll stick to super ones. So anyway, so this is, it turns out this to hold mod p squared. Now let me give another example. D is 4, and there we have the following congruence that fp1 is equal to AP. Again, we have a supercongruence, and we have a cube here. Well, it's not very meaningful unless I say what AP is. So AP is basically the coefficient of a modular form, and modular form is the following one. So we have a modular form that I like to call A of tau, which is given by the Dedekind eta function of 2 tau divided to the power 4, eta 4 tau to the 4, and that's basically it. This is a modular form of weight 4 with respect to the modulus of level 8, I think. Yeah. Anyway, so just for those of you who don't know this symbol, this is the so-called Dedekind eta function, and it's defined in this way. And Q, this is basically a product representation of the Taylor series of this function, and so Q is simply e to the 2 pi I tau. And this is a function which lives on the complex upper half plane, and this is all these remarkable transformation properties that go with modular forms. Now, you can expand this in terms of powers of this Q, and it turns out that this number AP here is precisely the pth coefficient of this Taylor series, of this Fourier series of this modular form. Which is quite surprising. So we started with some hypergeometric sum, and I get something which is of modular nature. And well, actually, it's a rather recent result. Kilburn, and I think in 2006, showed this particular result. But of course, it was observed experimentally many times before that, but it took some time before Kilburn actually gave a proof of this statement. It's a very long tour de force, which is quite impressive, and we finally got this result. Actually, when you look at, where is it? Yeah, this thing over here, actually, you can make a conjecture, and if you test it experimentally for different p's, then you find that probably this supercongruence phenomenon persists, in the sense that if you take S bigger than 1, you get congruences of this type. But considering how hard this one was, I'm not sure if anyone is going to do this very soon. But nevertheless, it's a conjecture you can try to work on. Okay, so this was the case D is 2 and D is 4. Let's continue to D is 6, and we can spend the whole afternoon. So let's do D is 6. So there we have another congruence, which is the following. The same type, and again, BP is a coefficient of a modular form. So BP is the coefficient of the pth coefficient of another modular form, and now I have to consult my notes because it's not explicitly given, but of a unique cusp form of weight 6. It has a more complicated expression of level 8 again. So it's again a coefficient of a modular form. And this result has been shown by, well, very recently by several people, Osborne, Straub, and Zudillen. And this was another tour de force which was even more recent than Kilburn. And we get this result. And conjecturally, well, experiments show that these congruences hold modulo p to the 6, so it's even more super than it already was. So, okay, so but we don't know how to do this. Okay, right, so now we can, of course, continue, but let me now give a general statement which holds more or less for all these, and that's a theorem which was proved recently by myself and Eric Delaygue. And we show that for all d greater or equal to 2, even, we have that fp of 1 is equal to fp of 1 modulo p to the squared. So we really get a supercongruence for all values of d, and then this fp1 is this mysterious unit root that I introduced in the beginning, and we can actually show that this congruence hold. Well, I should perhaps say that, in the case when d is odd, let me add this up. My d will mostly be even, but when d is odd, then we have also a result which is not necessarily at the point 1, but at the point epsilon. And this epsilon is simply plus or minus 1, depending on whether p is 1 or 3 modulo 4. So that's another slight generalization. So, well, I'm not going to give you the proof entirely, but let me state some, well, let me give the start of the proof at least, and then not finish it. So the proof start, what goes like this. It suffices to show that the following is true, that fp squared of 1 is equal to fp of 1 times fp of 1 mod p squared. So the little mysterious fp has disappeared entirely. Nevertheless, this is of course sufficient because we know that our unit root is actually the quotient of this one and this one. So the fp1 will be equal to that quotient. So fp1 is basically fp squared in this way. Okay, and this is of course all mod p squared. So we only have to show this, and you see that it looks quite simple. These are simply truncated polynomials, and then you have to work your way through the congruences. And it turns out that basically the proof is entirely elementary. There's some elementary identities. It's not very difficult. And at some point you reach the conclusion. I'm not going to spell it out, but I'd like to remark that a crucial ingredient, so basically the reason that supercongruences in this theorem exist are that, so I'm going to write down what the conclusion uses the symmetry fz goes to 1 over square z. So the symmetry of the differential equation. That's what it basically comes down to, or some finite version of it. Okay, so, well, after having these p to the 6 congruences, p squared seems a little meager, but it turns out that it's all you're going to get. So if you do some experiments, it will turn out that as soon as d is greater or equal than 8, then you will not get any more than congruences mod p squared, which is, well, it's something. But it holds for infinitely many values of d. Okay, so rather than giving you the proof, I prefer to give you some background on this mysterious unit root and tell you where it comes from. So I'm going to give you some background on this fp1. So maybe I should, yeah, I can So perhaps I should move over here. So to give you the background of this FP1, I have to introduce the hypergeometric motifs. So we're going to introduce one particular hypergeometric motif. And basically it's an arithmetic object which is motivated, that's the word it says, by hypergeometric function. And in this case, well, it's going to be of the following type, namely I guess you know the idea of a Gauss sum. A Gauss sum is something is a function of a character. So suppose omega is a character on the multiplicative group of the finite field with q elements, and then g omega is simply the sum over all invertible elements in the field fq of wx, and then here we get zeta p of the trace of fq over fp of this x, and zeta p is of course e to the 2 pi I divided by p. This is a Gauss sum with respect to a certain character on fq star. And we're going to use those. So in particular, let omega be a generator of the characters, multiplicative characters on fq star, and let phi be a character of order 2. It's a unique character of order 2, so it's like the mod p, this would be the Legendre symbol, and consider a function I call HQ, which is going to be the hypergeometric motif, and is defined as a sum over, well, actually, if omega is the generator of all the characters, then really fq star, the set of characters is basically given by the identity character and all characters up to the q minus second power. And so that's what we're going to sum over. So we're going to sum from n0 to q minus 2. And here we get g of omega to the m. Here we have g of omega complex conjugate to the power m divided by g omega to the power d. And then we add here omega of, and so this hypergeometric sum is going to have an argument which is t. And so here I'm going to have character values of this t. So this t here is supposed to be an fq star. So therefore you can take values of this character. And of course the values of the Gauss sum are complex numbers. The character values are complex numbers. So really this HQ is a function on fq star with values in the complex numbers, right? And actually they turn out to be integers because we take these arithmetic Gauss sums. Well, you can see the parallel with the ordinary hypergeometric functions. Namely, if you consider this Pochhammer symbol half m divided by m factorial, then you basically, the half is used to motivate this order 2 character that you have over here. The m is living down there, so basically this motivates this thing over here. And then this m factorial, well, that would be motivation for this Gauss sum, but you can use the functional equation for Gauss sums and get, well, you can bring it upstairs, and that will give you minus 1 to the power m of g omega, which is precisely, well, what's written there. And this g of phi is basically for normalization purposes. So it's independent of the summation index. Well, this is called a finite hypergeometric sum, and it was first introduced by John Green in the end of the 1980s, also by Nick Katz in his book on differential equations and analytic sheaves. And so they both had different versions of this finite hypergeometric sums. And so recently, well, quite a bit of interest has been paid, quite a bit of attention has to be paid to these hypergeometric sums for reasons that I will explain now. So, I guess if you, for example, if you have other hypergeometric functions, for example, if you have a parameter value, a fifth in your hypergeometric function, then of course you can write down a Gauss sum which has a fifth order character in it, much like we did over there. So you can sort of imagine how you can generalize this to more general hypergeometric functions with different parameter values. Okay, so let me erase this. So now let me mention one fact. This is the following fact. So I'm going to look at variety, an algebraic variety, which is this one. It's a funny one. And it turns out you can count points, FQ points on this variety, and I give you the formula for it. So we look at VT, we look at the points. Well, the coordinates are, you have a coordinate xi here, you have the inverse coordinate, so we'll be interested in coordinates which are non-zero, so we're going to be interested in the FQ start points in this way. And if you count the number of FQ start points, it turns out that this is precisely equal to q minus 1 to the d minus 1 divided by q minus 1 plus hq of t. So this finite hypergeometric sum occurs basically in a point counting procedure for this particular algebraic variety. And this follows from a paper of Henri Cohen, Anton Mallet and myself from 2 years ago, and where we give this kind of counting formulas for very general types of finite hypergeometric sums. This is just an example that I thought to give you an idea. Well, this point counting results motivates the following, namely, you know that, sorry.
An integer number, and on the other side you have NQ of t, where t is in the finite field.
This is an FQ. Yeah, this is an FQ star. It's a function from FQ star to C, and it turns out to have integer values. So it qualifies for counting, yes. So it has even integer values, so it qualifies for a counting function. Yeah. So really, basically, so this is the major part, and this is the correction which you have when which is the interesting part of the counting function. Well, you know that if you have counting results for varieties over finite fields, you can cook up the zeta function, and this is precisely what we're going to do. So, and instead of looking at the zeta function for this count, we're going to look at the zeta function for this hypergeometric sum, and it looks like the following. So define I call it Zp of t. Well, it's a very familiar construction. You take the exponential, and then you take the sum here, s is 1 up to infinity, of hp to the s of t divided by s by big T to the s in this way. And I always forget whether I should take a plus or minus here, I'm not sure, so I'll just leave it like that. And then it turns out, the result is that this function will be, well, this is small, will be this, where Rp is a polynomial Zt of degree d minus 2. If d is odd, it's slightly different. And I have to make a small provision here. I'll tell you in a moment, but basically this thing is going to be a polynomial. So I should perhaps add this. So it's not quite this. There's also an extra factor that we like to ignore, which I actually ignored here without you knowing, but it's something is ignored here, so I indicate it by this, and I'll explain that in a moment. Another point is that this Rp is a zeta function of this counting function, you could say, and it has all the properties that, according to the Delaygue conjectures, it has a functional equation, and also the absolute values of that polynomial, they have the same value. So let me write that down. So I'm switching boards here. So this Rp of t, well, it's going to have a factorization, and I'll write it in this way. So it's 2 minus 1, it has 1 minus mu I times t in this way, and the mu i's are complex numbers, but you know that according to the Delaygue conjectures, they should all have the same value, and it should be some certain power of p, which turns out to be d minus 1 over 2. And this d minus 1 is called the weight of this part of the zeta function. So, well, I'll just say it, it's called the weight. So, and by abuse of language, I will call this mu i's, I will call them the zeros of this polynomial. Even though the t should be over there in order for this to qualify as a polynomial, but I'll just abuse language in this sense. And what I'd like to do now is give, so maybe I should say what this little twiddle here means. Actually, there's an extra factor of a weight which is different from d minus 1, which I ignore, and I do this by introducing this. So I keep the weight d minus 1 part, and that's that thing over there.
So, Frits,
yes?
In general, this Rp of t in functionality for other representatives should be a rational function.
Yes, yes.
So here there is a true miracle, or is it the case that the factor that you are hiding is encoding this rationality?
So maybe I should say, hang on, I'm making a little mistake here. So in general, we don't need this. So if t is not equal to 1, then we don't need to put this here. Then you simply get a polynomial. However, in the case when t is 1, which is the case I'm going to be interested in, and actually I'm going to force this interest by putting a 1 here, then you get, it turns out that it corresponds to a singular point of the differential equation, so it causes a little extra factor that you don't really, that doesn't really have your interest, so I cut it out, I just ignore it here. So, but it's a small detail, I think. Okay, so we get those, and what I do is display a few of these functions for you in the next few slides. So where would you get D6? Yes, so we're at D6. So let's write down some of these. Yes, I should perhaps erase this. So let's take the case D is 4 once again, which you already saw over there, but here's D is 4. What's going to happen then? Well, it turns out that the D, in case D is 4, ZPT is going to be the polynomial 1 minus AP t plus p cubed t squared, in this way. Now, if this is the AP which occurs as a coefficient of a modular form, and here we get a p cubed, which corresponds to the fact that this is d minus a half d minus 4, but divided by 2 because we have a square there. So we get this, and well, if p does not divide AP, you can say something about the p-adic evaluations of the zeros of this polynomial simply by drawing the Newton polygon. So the Newton polygon is simply here, well, that corresponds to the 1. P does not divide AP, so in degree 1 we have this, and 1, 0, and 2, and here we have 3, so we get a slope 3. So that means there's 1, 0, which is a unit, and that's precisely the unit root. Okay, and there's another 0, which is divisible by p cubed, and well, basically it implies that the unit root modulo p cubed is equal to this coefficient, So that explains that you have this result of Kilburn over there, this AP mod P cubed result. Okay. So it has a modular origin, and it comes from the zeta function of this hypergeometric motif. Yes?
Then you have to correct your conjecture and keep the unit root there, not AP. If you want it modulo P to the power 6, because that's not 4, plus your first 4, there should be the unit root.
Maybe. Yeah, okay, maybe you're right. Okay. Thank you. Thank you. Yeah. Okay, so this is DS4. Then we get DS6. And so the polynomial will have degree 4. And it turns out that this polynomial factors into two quadratic factors. So in this case, ZP of t is going to be 1 minus p times APT plus p to the 5th t squared. And 1 minus BP t, sorry, plus p to the 5th t squared. And now we have the same story all over again. If we look at this, so this is the BP which we, well, I just erased it. So these are the coefficients of that particular modular form, for which presumably, oh sorry, this should be a 6, I think. Or should it 5? No, it's 5, sorry. Yeah. Yes. So now you see that these are the coefficients which I showed before, also coefficients of modular form. And again, you have the same thing. You get something now with a slope of 5, which accounts for the congruence modulo p to the 5th. And now there's another factor. So it turns out that this really factors into two factors. So this factor, it has the APs, and it's no accident that I write the same coefficient here, because they turn out to be the same as this AP is the same as this one. It's again coefficient of a modular form, of that particular modular form, which corresponds to that one. And well, this is very strange. So really, this zeta function, it has a unit root. Well, at least if p doesn't divide BP, but it also has a root which has valuation 1 over p, which is very funny. And Vadim Zdudilin pointed out to me that if you have such a phenomenon, you even get another congruence, and the congruence is like this. So the fact that you have this, well, I don't think anyone knows how to prove this, but it's nice to mention it. To the 6, k factorial to the 6th is equal to p times AP mod p to the 4th. So if you draw the Newton polygon of this, I will say I get a slope 1, and the difference here is 4, get a slope 4, and this is precisely the p to the 4 that corresponds to the particular slope. And you get this, this funny congruence. And I don't think anyone has any idea how to show this, but it's again something you can observe numerically. Well, we can go on for a little while, so let's go to DS8. Well, there's still some room. And it turns out that this is equal to 1 minus p times Cp of t plus p to the 7 t squared. And here we get something okay, well, because of the functional equation for the zeta function, you get the alpha p occurring in front of the t cubed and in front of the t. So they're kind of reciprocal polynomials. And well, this doesn't factor any further. And now the thing is that, again, if p does not divide alpha p, then you find you have a slope 0, and you get a slope 2, which basically accounts for the mod p squared congruence that Eric and I got in the theorem that I mentioned. So that's all good, and this, well, contrary to the previous cases, this has no real interpretation in terms of modular forms, at least not that people know of. Probably it corresponds to some Ziegel modular form or some other higher dimensional modular form, but people have no idea which one to take for that, and also there's no idea how to attack that, but at least you have this thing, and you have the congruence. And also, well, you have a similar phenomenon there. The CP is really the coefficient that corresponds to the modular form, this thing to the power 12. And it turns out that also you have a similar congruence for CP as the one here. You simply replace the 6 by the 8, and then experimentally you find you get an analogous congruence. So it's all persistent. Now, let me... Oh, perhaps I should say something. Or maybe not. Okay, so let me do the last case for you. So that's the case D is 10. In case D is 10, we get another factorization. And the thing is that it's already a miracle that you have this factorization at every stage, because that is not at all obvious. So I get something of this nature. T plus p to the 18, t to the 4th. Well, okay. But I guess the pattern is going to look pretty familiar. So here we have some 4th degree factors in general. This is a 10. T cubed plus p to the 18, t to the 4. Okay, so here we go. Now you recognize, of course, the unit root that I introduced in the beginning, because here if p does not divide alpha p, this corresponds to slope 0, and all the other coefficients point out to something of higher slopes. So it's a unique root of unity. Also, there's a unique 0 of the zeta function, which has valuation 1, p-adic valuation 1, and it sits in here. And of course, the idiotic thing again is that if you do this congruence with a 10 instead of a 6, again this congruence holds. So it seems pretty persistent. And you see that the difference between these two exponents is 3, so you expect here a congruence modulo p cubed to hold of this nature. I'm not going to write it down.
But what stands for AP in this context?
AP. Alpha p. This alpha p is this? Yeah.
In your conference modulo p to the 4.
Oh, I see. So it will be this. So in yes. So this AP is going to be congruent modulo p squared to the unit root of it, right? Because of this Newton slopes. And similarly, you have something here, the modulo p cubed, that this valuation 1, 0. Is going to be equal to this one, modulo p cubed. So you can put these coefficients in the congruences. I guess that's what you mean. Yeah.
And there's, in general, the unit root there.
Yes, absolutely. Yeah. Okay, so we can go on for a while, and then you can conjecture, for example, that this type of congruences is also very persistent. Well, I have to, officially, you have to prove that for even for higher Ds that you have this factorization. We don't have a proof yet. I think you can give this, so usually when people talk about hypergeometric motif, some people point out a variety which is raised basically at the back of this zeta function computations or cohomology computations. And then, so that variety which you see over here would be the motif which is behind this particular finite hypergeometric sums. That's, well, you can do that. And the thing is that if you take t as 1 in this case, there's an interesting correspondence between this variety and itself, which also acts on the cohomology, and it corresponds to the involution of the differential equation that I showed you in the beginning. So this symmetry of the differential equation can be explained geometrically by looking at this variety. And this symmetry is also probably, although I haven't worked it out completely, is responsible for this factorization of the zeta function into these two factors. Okay, now to end with, I like to make a little bit more advertisement for hypergeometric motifs. And so this whole story with hypergeometric motifs was initiated by Fernando Rodriguez Villegas, I'll just abbreviate it by FRV, and he started a long-term project in which had the goal to produce global L-series and check, for example, whether the global functional equations hold and other properties, whether it can be continued analytically throughout the complex plane and properties like that. And so Fernando started this, and if you're interested in studying global zeta functions or L-series, then the supply of examples is very small. Actually, you can start with, for example, the modular forms, which are well known, or the L-series that correspond to elliptic curves. Well, things are well known for that. But if you go beyond that, it's even hard to get your hands on a big series of examples. And using these hypergeometric motifs, it's possible to give a very large supply of interesting global L-series, for which you can then study the properties. And, well, proving is, of course, one thing, but at least you can verify all the conjectures that exist in this area. So let me give one particular example. So Fernando was particularly interested in this hypergeometric function, which is famous for people working in mirror symmetry. It's the one that occurs in the work of Candelas, de la Osa, and Parks, Green Parks, I forgot all the names. Anyway, it's a famous one in mirror symmetry. And so what Fernando did was study the L series that corresponds to it. So what he did was basically take phi character of order 5, consider the hypergeometric sum. Well, like it's a parallel of what I introduced earlier on, A1 over 4, and then we have some g omega, and then we get omega t to the power m. So this is the finite hypergeometric analog of this hypergeometric function which you see over here. Cook up the L function that corresponds to it, so we call this HQ of t. So you cook up the zeta function or the L function, so the zeta function corresponding to its ZP of t, which is simply, again, this exp of this sum. To the s greater or equal than 1. Again, you get a polynomial, and now comes the interesting thing. So these are local factors of something that you want of global L series. You're going to use these factors. So now we're going to choose a prime. Such a prime is not equal to 5, because that's a very bad prime, with the 5 being over there. And also you assume that t and t minus 1 have p-adic valuation equal to 1. And primes that have that property are called good primes. So start with a good prime, then you can always, you can cook up a product. So this is a good prime. So you take the product over all good primes of 1 over Zp, p to the minus s. This is the usual way of cooking up a zeta function. And well, I like to call this the good part, S. And of course, there's also a bad part. But there's no way of knowing what you have there. Okay? But anyway, conjecturally together, they should form a global L series which has all the properties that people expect, for example, analytic continuation throughout the complex plane and the functional equation. And the only thing is, well, to guess what the right factors are and what the right parameters are going to be. Now, it's a very miraculous project, I think. It turns out that if you have an L series like this, then, and you have, well, sufficiently many factors, you can already predict quite precisely what, for example, the values of the L series at certain points will be. Also in the region where the thing conjecturally, well, is not known to converge. Also, you have this functional equation, and what should a functional equation look like? Well, let's call this L series. It's going to be the product of the good part and the bad part. And of course, you know that you have to normalize it with 2 pi times the conductor of n to the power minus 2s. And then you have to introduce some gamma factors. And there's a whole science of cooking up what gamma factors are in different cases. So for this case, this mirror symmetry case, you should probably take this one. And then the thing is that you have a functional, so this should continue to the whole complex plane, and then it's expected that you have this functional equation for all s's in the complex plane. And so what Fernando did, and his co-workers, was basically, well, evaluate this function at different points. And, well, they didn't know what this value was, they didn't know what these factors were, but they guessed them. They made several guesses and computed the values until the parameters were chosen in such a way that this equality would hold up to 50 decimal places or something like that. And that would tell them that they had picked the right parameters, and in this way, conjecturally, they know precisely what the global L function is and what, for example, the conductor of this hypergeometric motif is. So this has been going on for quite some time, and as a result, there's a package in Magma which basically computes, for example, these polynomials for you. It also tests these conjectures. If you have a hypergeometric motif that you want to test whether the conjectures hold, it tests it for you. So it's a big package. It's very impressive work. And okay, well, in the next lecture, you're going to see an alternative approach. I'm not going to say much more about this because Kieran will do that. But anyway, I'd like to close here. Thank you.